is Algebra Lesson 6-8, Graphing Absolute Value Equations. The absolute value graph is a V-shaped graph that points upwards or downwards. Now, we've done some of these in Chapter 5 when we were looking at just graphing in general. But today we're going to look specifically just at absolute value graphs. A translation is a shift of a graph that is shifted horizontally, vertically, or both horizontally and vertically. All right, you need to get out a piece of graph paper, and if you have colored pencils, those would be handy as well. What we're going to do is we're going to graph the following three equations. Y equals the absolute value of x, y equals the absolute value of x plus 2, and y equals the absolute value of x minus 4, all on the same coordinate plane. We're going to put them in different colors, however. I'm going to start with y equals the absolute value of x. Okay, y equals absolute value of x, I'm just going to make a little x and y table here. And I can tell you when x is negative 3, the absolute value of negative 3 is positive 3. When x is negative 2, the absolute value of negative 2 is positive 2. When x is negative 1, the absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. And the absolute value of 3 is 3. If we were to graph this equation in purple on our x and y axis, and again, you would need to use straight edge. I'm going to have a little trouble because I can't put the straight edge on my smartboard, or at least I haven't figured that out yet. So if I'm going to go negative 3, positive 3, negative 2, positive 3, negative 1, positive 1, 0, 0, 1, 1, 2, 2, 3, 3. This is what we call the parent function. Okay, it's the graph of y equals the absolute value of x. If we're going to graph the next graph, y equals the absolute value of x plus 2, I'm going to do this in blue. Okay, again, I'm going to make an x and y table. I'm going to make it an abbreviated x and y table. So if I'm going to do the same points, negative 3, negative 2, negative 1, 0, 2, and 3. If x is negative 3, the absolute value of negative 3 is positive 3, and 3 plus 2 is 5. The absolute value of negative 2 is 2, and 2 plus 2 is 4. Absolute value of negative 1 is 1, 1 plus 2 is 2. 1 plus 2 is 3. Let's do that right. 1 plus 2 is 3. Absolute value of 0 is 0, 0 plus 2 is 2. Absolute value of 1 is 1, and 1 plus 2 is 3. Absolute value of 2 is 2, 2 plus 2 is 4. Absolute value of 3 is 3, and 3 plus 2 is 5. If I was to graph this, negative 3, positive 5, 3, 1, 2, 3, 4, 5. Then I go negative 2, positive 4. And then negative 1, 3. 0, 2. 1, 3. 2, 4. Oops. 1, 3. 1, 2. Let's get those in the right spots. 1, 3. And 2, 4. And 3, 5. There's the graph of y equals the absolute value of x plus 2. And for this last one, I think I'll do this one in green. Y equals the absolute value of x minus 4. Again, I'm going to do an abbreviated x in my table. And again, I'm going to use the same points, negative 2, negative 2, negative 1, 0, 1, 2, and 3. So the absolute value of negative 3 is 3, and 3 minus 4 is negative 1. Absolute value of negative 2 is 2, and 2 minus 4 is negative 2. Absolute value of negative 1 is 1, and 1 minus 4 is negative 3. 0 minus 4 is negative 4. 1 minus 4 is negative 3. 2 minus 4 is negative 2. And 3 minus 4 is negative 1. I was to graph this, negative 3, negative 1. That's there. Negative 2, negative 2. Here. Negative 1, negative 3. 0, negative 4. 1, negative 3. 2, negative 2. 2 is negative 1. If I was to graph this graph, this would be the function of y equals the absolute value of x minus 4. All right, so we've graphed all three graphs on our x and y axis. How are these graphs the same? Well, obviously, hopefully, you're seeing that they're all the same shape. They didn't get any wider or any narrower. They didn't flip over. They didn't rotate. They just moved. And hopefully, you also noticed how are they different? They moved up and down. If the purple graph is our parent function, when we added 2 to the absolute value, right here, you'll notice the graph moved up 2 units. When we subtracted 4 from the absolute value, you'll notice our graph moved down from the parent function 4 units. Okay, so how are these graphs the same? They are the same shape. Same shape and size. And how are they different? They moved up or down. In other words, they were translated. How can we roll all this up into a statement to make it so that you can understand, so that we can summarize what we just did? Well, let's look at this. The vertical translation of an absolute value graph, that means the up and down translation of an absolute value graph. If the graph of y equals the absolute value of x plus k, where is a translation of the parent function y equals the absolute value of x. If you let k be a positive number, then y equals the absolute value of x plus k translates the graph up k number of units, while y equals the absolute value of x minus k translates the graph down k number of units. If we go back to our graphs here, you'll clearly see the purple graph was our parent function, the blue graph translated up k units, this was k right here, and the green graph translated down k units because the blue graph was plus, so it went up, and the green graph was minus, so it went down. Now, let's take a look at something slightly different. Here's a couple more equations, and you'll notice these equations are a little bit different than the equations we had before. Again, we're going to start with the parent function of y equals the absolute value of x. I'm going to put that in blue. Hopefully you remember that that just goes like this and like this. That's the parent function of y equals the absolute value of x. Now we're going to take a look at what happens when we have more than just a variable in the absolute value. What happens when we have other numbers in the absolute value besides just the variable itself? So let's take a look at y equals the absolute value of x plus 2. I'm going to do this in red. Again, I'm going to try to do an abbreviated x and y table. And I'm going to use, I think I will go with -3, -2, -1, 0, 1, 2, 3. Just like I did before. Okay, so now I need to take my number that I'm placing in for x, add 2 to it, and then take the absolute value. That's what basically this is saying. Okay, so I will take -3 plus 2 is -1, the absolute value of -1 is positive 1. -2 plus 2 is 0, the absolute value of 0 is 0. -1 plus 2 is is 1, the absolute value of 1 is 1. 0 plus 2 is 2, the absolute value of 2 is 2. 1 plus 2 is 3, the absolute value of 3 is 3. 2 plus 2 is 4, absolute value of 4 is 4. 3 plus 2 is 5, and the absolute value of 5 is 5. So I will graph this. -3, 1. -2, 0. -1, 1. 0, 2. 1, 3. 4. 3, 5. So if you just graph just the dots itself, it would look like a giant check mark. However, we want it to look more than just like a giant check mark so that you can actually understand it. So I'm just going to say, okay, what would happen if I added a couple numbers, -4 and -5? Absolute, okay, -4 plus 2 is -2. The absolute value of -2 is 2. -5 plus 2 is -3. The absolute value of -3 is 3. So if I did that, this would continue going this way, wouldn't it? Now it doesn't look like a giant check mark. It looks just like the blue graph, except for it's been moved. Okay? And we'll talk about how it's been moved in just a minute. Let's go to the last graph. Y equals the absolute value of x minus 2. And again, I'm going to do this in a different color. If I choose to put this in purple, again, I'm going to do an abbreviated x and y table. -3, -2, -1, 0, 1, 2, 3. I may need to add some numbers later to keep it from being a giant check mark, but I'll do that later if I need to. -3 minus 2 is -5. The absolute value of -5 is positive 5. -2 minus 2 is -4. Absolute value of -4 is 4. -1 minus 2 is -3. The absolute value of -3 is 3. 0 minus 2 is -2. Absolute value of -2 is 2. 1 minus 2 is -1. The absolute value of -1 is positive 1. 2 minus 2 is 0. The absolute value of 0. 0. 3 minus 2 is 1. The absolute value of 1 is 1. I'm going to add a couple and add 4 and 5 here. 4 minus 2 is 2. The absolute value of 2 is 2. 5 minus 2 is 3. The absolute value of 3 is 3. So, -3, 5. Right there. -2, 4. -1, 3. 0, 2. 1, 1. And 2, 0. And then 3, 1. 4, 2. And 5, 3. So it's not a giant check mark after all. It just happens to be the same graph, but it moved again. Okay. The red graph was the absolute y equals the absolute value of x plus 2. The purple graph is y equals the absolute value of x minus 2. So for your poor little brains, it kind of works kind of backwards, doesn't it? You think the red graph, since it says plus 2, should move to the right 2. But since you're taking an absolute value, it's going to basically shift everything to the opposite of what you're thinking. So x plus 2 shifts the graph left 2 units. The minus 2 shifts your parent function right 2 units. Okay, so we have these graphs that look just like this. Again, how do we summarize this? Horizontal translations of absolute value graphs. For a positive number h, y equals the absolute value of x plus h. Translates the graph y equals the absolute value of h, or excuse me, x, h units to the left. So if you add it, it goes to the left. If you subtract it, it goes to the right. This is something that's very important. Obviously, I've highlighted it in these nice green color, so you should copy this into your notes. Now, applications of this. We can write an equation for each translation. If I gave you y equals the absolute value of x, and I ask you to translate it into an equation, and I tell you, okay, we're going to go 9 units down. If you remember, up and down means you keep the only thing in the absolute value is the variable. Left and right means everything's inside the absolute value. So if I want to go 9 units down, that would be the y equals the absolute value of x minus 9, because we're 9 units down. If I'm going 10 units left, remember, left and right means everything's in the absolute value. So that's going to be y equals the absolute value of x. I'm going left, which implies negative, but means the opposite. So x plus 10. 4.5 units right. Y equals the absolute value of x minus 4.5. It's going right, we're going to subtract it. 8 units up. Y equals the absolute value of x. That's the only thing in the absolute value, plus 8. They're really easy equations to write. And they're not really hard equations to graph either. Let's say we're supposed to translate the following or graph the following by translating y equals the absolute value of x. If you want to, you can use and put on the parent function. Some people have to draw the parent function and then move it. Some people can draw their equation without drawing the parent function. I'm going to always draw the parent function in red because I think it's helpful for people. Remember, the parent function just starts at 0, 0. You go up 1 over 1 every single time, up 1 over 1, up 1 over 1, up 1 over 1. Here, up 1 over 1, up 1 over 1, up 1 over 1. Makes a giant V. There's my parent function. So if I need to translate that, so y equals x plus 4, that's going to be a horizontal shift, and it's going to go left. So I'm going to put that one in green. So I'm going to go 4 units to the left. 1, 2, 3, 4. So here's where my vertex is. Up 1 over 1 again, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 until I run out of space. So this green graph is y equals the absolute value of x plus 4. Very simple. You no longer need to make x and y tables if you know how to translate your absolute value parent function. The parent function is y equals the absolute value of x. So look at the second one here. Y equals absolute value of x again. So I'm going to move this one to right so far down on the bottom of the page. Okay, my absolute value of x, there's my parent function. Right there. Y equals the absolute value of x. Plus 4. That's a vertical change because the only thing in the absolute value is the variable. So I'm going to put that up 4 units. 1, 2, 3, 4 units up. And if we had more graph paper, it would look something like this. Right? So this would be y equals the absolute value of x plus 4. If I was drawing on my own graph paper, I would probably put my x-axis down here so that when I shifted it up, I don't have to use so much paper. Your x-axis does not always have to bisect your y-axis exactly. Let's go back to writing equations for translating y equals the absolute value of x. What happens if we decide we want to translate both horizontally and vertically? Let's just have a little guessed problem here. Let's say I want to add a problem 5 right here. We'll want to go 6 units left and 3 units down. We're going to do both of them together. And if that was my case, y equals left and right means everything's in the absolute value. Left means I'm going to go a plus, so x plus 6. 3 units down is outside the absolute value, and it's minus 3. So all you do is horizontal goes first, vertical goes second. Simply done.